Imagine thousands of computers scattered across the world, not knowing or trusting each other, all trying to agree on a single shared record. Every node holding a copy of the ledger needs to update its records in the exact same way, simultaneously, without a central manager to make the final call. Computer scientists formalized this in 1982 as the Byzantine general's problem. How do you coordinate a loyal army using unverified messengers who might be traitors trying to sabotage the plan? In a digital network, the traitor's tactic is the double spend. Digital files can be copied perfectly, allowing a bad actor to spend the same digital currency twice before the network settles the first transaction. Without a central authority verifying the data, if a single node accepts a fraudulent transaction, the network fragments into competing, contradictory histories. Network consensus is the engineering protocol that solves this problem. It is the mandatory, automated mechanism preventing a total collapse of the shared data. Building that consensus mechanism requires strict architectural compromises. There is no single, universally optimal solution for these highly complex distributed systems. This structural law is the blockchain trilemma. Every decentralized system balances three properties: security against attacks, scalability for high volumes, and decentralization for permissionless control. It's mathematical. Stretch the network to maximize scalability, and you inevitably fracture its decentralization. Evaluating any blockchain requires looking at this framework and plotting exactly what physical or structural sacrifices it made to achieve its throughput or its security. Satoshi Nakamoto's original solution to trustless networking was to use thermodynamics. Proof of work makes disagreement physically expensive. Miners compete to append the next block by utilizing raw computing power to guess a random cryptographic number, known as a nonce. This maps the deliberate asymmetry of the design. Finding the hash requires massive trial and error. Verifying the output, however, is computationally trivial. That asymmetry allows the network to instantly verify the math and reach strict agreement without trusting the miner. The network automatically recalibrates the puzzle's difficulty every 2016 blocks. If more miners join, the math gets harder, enforcing a strict 10-minute block interval. Miners invest in this hardware because the protocol rewards honest validation with newly minted currency and transaction fees. The cost of that honesty is roughly 175 terawatt-hours of electricity per year. Rewriting the blockchain requires outpacing the entire network's combined computing power, making an attack economically irrational. Plotting proof of work onto the trilemma places it midway along the edge between security and decentralization, intentionally abandoning scalability. Bitcoin's 10-minute bottleneck is a deliberate architectural feature. Absolute security requires sacrificing speed. As blockchain applications grew to support complex code, that thermodynamic limit became a hard ceiling on scale. In September 2022, Ethereum executed the merge, reducing the network's energy consumption by 99.8% overnight. The switch to proof of stake replaced physical energy consumption with economic collateral. To participate, validators deposit 32 Ethereum into a smart contract, locking it as a network bond. An algorithm divides time into 12-second slots. One validator is randomly selected to propose a block, and a 66% network vote finalizes it. If a validator proposes fraudulent data or conflicting votes, the protocol triggers a punitive mechanism called slashing. Rather than just rejecting the bad data, proof of stake actively destroys the attacker's bonded capital. The system traps malicious actors in a mathematically guaranteed financial loss. The barrier to entry, however, drives users to pool their funds with large liquid staking platforms, consolidating validation power into fewer operational entities. On the trilemma, proof of stake moves the plot point inward, gaining scalability but generating new friction on the decentralization axis. It abandons physical energy anchors for architectural efficiency, relying on game-theoretic financial ruin to police the network. Global, anonymous participation inherently limits speed. Coordinating thousands of nodes worldwide guarantees slow consensus. Delegated proof of stake bypasses this bottleneck by structurally shrinking the active validator set. Token holders use their assets as voting weight to elect a closed committee of just 21 to 101 block producers. A smaller committee requires less time to coordinate. Block generation drops from 12 seconds to half a second. Proof of authority pushes this logic further for enterprise networks, removing capital stakes entirely in favor of real-world identity. blocks are processed by a fixed rotation of known, legally vetted corporate or institutional entities, enabling high-speed, zero-fee ledgers. Plotting these variations pushes them violently into the scalability corner. They achieve enterprise-grade speed by dropping the requirement that participation be permissionless. In distributed networks, time creates latency. Waiting for nodes globally to sync their clocks to agree on the exact order of events causes massive delays. Solana approached this with proof of history. It operates not as a replacement for proof of stake, but as a supplementary cryptographic clock running alongside it. This maps the sequence. Hashing outputs are fed continuously into the next input, embedding a verifiable timeline directly into the data. Validators no longer waste milliseconds verifying the order of events, pushing throughput up to 65,000 transactions per second. Maintaining this speed requires validators to operate highly expensive, specialized server hardware. Proof of history bypasses the latency limits of the Trilemma, but moves the centralization risk directly to the hardware layer. A mathematically perfect consensus mechanism with zero physical trade-offs defies the laws of distributed computing. This master diagram plots the available landscape. Bitcoin uses proof of work to prioritize the thermodynamic, battle-tested security required for global value settlement. Ethereum balances economic security with the processing efficiency needed to maintain massive smart contract ecosystems. Delegated and authority models provide the hyper-fast processing necessary for private enterprises that do not require absolute decentralization. Evaluating a network requires identifying the strict mathematical trade-offs encoded directly into its consensus layer.